Hey everybody, today's video is going to be about something called Bayesian statistics, and specifically I'm going to be talking about something called Bayes' theorem. Now I'm just going to quickly write down the actual equation for Bayes' theorem, and then we're going to get into a couple of applications. So I won't explain what these mean just yet, but this is what the equation looks like. This is a statistical equation based on two events that can occur, A and B, event A and event B. Alright. Cool. And in this context, P as a function just refers to the probability that something will happen. So, for example, this thing here means the probability of A. This thing here means the probability of B. This here means the probability of B given that A is true, or the probability of B given that A has happened. And this means the probability of A given that B has happened. Now, I want to talk a little bit about how this equation is derived and whatnot. But to start with, we're going to start with a puzzle. And I think I might have actually discussed this once before on this channel. Here is the puzzle, and I've got it written down here. Todd is quiet and shy. Is he more likely to be a librarian or a sales rep? And taking time to think about this, because the answer won't be as obvious as you probably will think. So we know that Todd is shy. And so an original, sorry, I shouldn't say original. A very normal thing to think here would be, well, shy people are more likely to be librarians, right? Because librarians are typically shy. Sales reps aren't very shy, right? So you might just answer librarian and think you've solved the case. But you're missing one crucial fact, which is that there are way more sales reps than there are librarians. And that actually matters. This is something called the base rate fallacy, where you sort of forgot to consider the relative base rate of these two things, namely being a librarian and being a sales rep, and you get so caught up on the fact that Todd is shy. So the answer here actually is sales rep, if we grant that, say, there are 1,000 times more sales reps because there are librarians, which I think is reasonable. I mean, some firms will have a lot of sales reps, but you got one librarian in every town, something like that. So let's give these things values, and we're going to do a bit of guesswork, of course. So let's say that S means let's say that S means shy, or S means that Todd is shy, and L means that Todd is a librarian. Alright, so let's start with, what are they asking us? Well, they're asking us to find what's the probability that Todd is a librarian given that he is shy. That's what we're trying to figure out. So what do we know? Well, let's start with what's the probability of being a librarian? Well, it's going to be very, very low, right? So let's just say 0.0001. Let's say something like this, right? It's a low number. Now, what's the probability of someone being shy given that they're a librarian? Now, this is how a lot of people originally see the question, is that they're being asked this, but you're not, you're being asked this, which is two very different things. If you take any random librarian, the odds that they're shy is probably quite high. It's not going to be 100%, but let's say, I mean, librarians are quite shy, right? So let's say 0.95. And the final thing we need to calculate here, or estimate I should say, is what's the probability of someone just being shy generally? It shouldn't really matter for our equation. Let's just say maybe 30% of people consider themselves shy. So something like this. Cool. And now we have the numbers to fill into our equation. Well, we've got P of B given A. That's the same thing as saying shy given that they are a librarian. So it's going to be 0.95. And then let's put in here the probability of A, or in this case, the probability of them actually just being a librarian, given no other factors. It's going to be this very, very small number. And then the probability of them just being shy will be 0.3. Cool. And now you can see that, well, even if this number here is quite large, which it is, it doesn't matter because this number here is so small. they sort of cancel out. And in fact, the fact that this number is so small, the fact that you're so unlikely to just be a librarian in general, means that the fact that he's shy doesn't actually help us as much as the fact that he's probably not going to be a librarian anyway. Another way that we can think about this is that being shy slightly predicts being a librarian, but being a human strongly predicts being a sales rep, because humans are more likely to be sales reps than librarians. So we're putting way too much emphasis on this shy fact, when the fact that being a librarian is already so rare does most of the heavy lifting for us. Well, let's be fair, and let's compare this to the sales rep study. Obviously, that would be the fair way of doing it. So let's add a new thing called R, which means the probability of being a sales rep. Cool, and let's do some more calculations. So let's just say, what's the probability of someone being shy given that they're a sales rep? Well, that's probably going to be a bit less. Let's say, I mean, sales reps are quite extroverted, so let's be generous. Let's say it's going to be 0.05. About 5% of sales reps consider themselves shy, which is way less than our figure for librarians. And what's the probability of someone just being a sales rep in general? Well, it's still going to be very small. I mean, there are a lot of jobs, but in order to make my point, it's going to have to be a lot bigger than librarians. Let's say there are 100 times more sales reps than librarians. I'm just going to put this value at 0.01. It's 100 times the difference. Cool. And so now we can calculate the probability of a sales rep given shyness. Plugging in our values. Now our top value here has gone down 0.05, but this value has gone up by quite a bit. Now it's just 1%, and it's still being divided by 0.3. So you can see how this 0.3 doesn't really matter, the probability of being shy. If we're comparing these two values, we can sort of just, forget these things. What we're really comparing is this to this. And you can see that, of course, this here is bigger, even though this value is a lot smaller, but the fact that this value has way more of an impact, right? Because it's 100 times this value. Cool, all right, and that was my first example. So the answer is Todd is more likely to be a sales rep, and it's just because there are more sales reps. Now, with that in mind, I'm going to give a second problem very similar that also uses this idea of Bayes' equation. It's quite a popular one. It's to do with medical testing, and we're also going to use Todd as our example. So let's say that there's some illness or some disease or some sickness. Let's say that there's a sickness, and let's say it affects 1% of the population. So another way of saying this is that 1% of people have this sickness, right? How 1% of people have it? And let's say there's a test for the sickness, and the test has a 99% accuracy. So it's a 99% accuracy, and then let's say Todd tests positive for the sickness. And that's all the information we have, and the question is Todd more or less likely to have the sickness? What can we say about Todd's actual chance of having the sickness? And if you want to pause and have a think about it, I recommend it. Just to give a little clue, the answer is not just 99%. It's not that simple. Cool. All right, so we'll get into an answer. First, it's important to state what we mean by 99% accuracy. What this means is that if you do the test on 100 people, for 99% of them, or 99 of them I should say, it's going to give the accurate result. So this doesn't mean that if you have this sickness, this means that if you have this sickness, there's a 99% chance that it will figure it out. But it doesn't mean that if it says you have this sickness, there's a 99% chance that you have it. So hopefully you can see how these are two very different things. Again, we're getting into this idea of event A given event B is very, very different from event B given event A, right? These are two very different things, right? People confuse them a lot. This 99% is sort of like this one, but we're being asked for this one. So let's give a little example of what this sort of thing would look like. Well, let's say it affects 1% of the population. So let's imagine there's 10,000 people, right? Imagine 10,000 people, and they're picked uniformly at random. So what can we say about these 10,000 people? Let's say they all get tested. So how many of them actually have the sickness? Well, it affects 1% of the population. So we'll say 100 people are sick. So how many aren't sick? Well, it will be what? 99900. Sorry. Yeah. Good. Aren't sick. So are healthy. Now, let's say everyone gets tested. Well, of the 100 sick people, if everyone gets tested, how many of them are going to test positive? Well, it's got a 99% accuracy, so we're going to have 99 positive results. 99 positives. Now, for the 9,900 people who are healthy, they all test, and 99% of them have an accurate result, which means that 1% of them get the wrong result. So what's 1% of them? Well, it's 99. So 99 people get the wrong result, which in this case would be positive, because they should be testing negative. So 99 of them will test positive. So this gives us a clue as to what our answer is. Well, what our answer is, out of the 10,000 people, if we look at all of the positive tests, half of them were sick and half of them were healthy, which is quite an unintuitive result. But the idea here is that this test actually doesn't give us much information. It's 50-50. It's 50-50 that you're going to be in this group of false negatives or this group of false positives. Now, to put it into our equation again, which we can do, let's say, I'm trying to think of a way of doing this. Let's lay out what we know. So P of S can mean sick. What's the probability of being sick? Well, it's 0.01, right? 1%. Now, what's the probability of getting a positive given that you were sick? Well, that's just another way of asking what's the accuracy rate, so it's 0.99. What's the probability of just getting a positive straight up? Well, this is going to be a bit more math because it's going to involve two different scenarios. We need to count up the false positives and the true positives. But if I do the math, it'll end up with 0.99 for the positives. It will affect this many people. And then to do the false negatives, it's going to be timesing this. Cool. And now we have what we need to do to calculate our thing. What they're actually asking us is what is the probability of them being sick given a positive result. So plugging in all these values using our equation, we're going to get, it's going to be 0.01 times 0.099 times this stuff, which is, I won't write it in, but it's going to be this whole thing here. And what you'll notice here is that these are actually the same term twice, just written differently. And it's also the same as this term. So it's just 2 of something over 1 of something, which is going to simplify it to 1/2, which we got before. That's another way of picking the answer. So the answer is definitely 1/2. And you can see we've sort of gotten that in 2 different ways now. So yeah, so Bayesian statistics, you get a lot of really weird and counterintuitive results. It's a very human thing to confuse these different probabilistic terms, to confuse possibility that A implies B with the possibility that B implies A. I've got one more quick thought about this. So I've got 2 more quick thoughts about this. So this formula here, one thing I can do is I can play with it, and I can try to rearrange some of the numbers. So what happens here if I just do some algebra? Well, let's times both sides by the possibility of B. Sorry, I should be saying I should be saying probability here, not possibility, because they are different. I times both sides by P of B, I end up with this. Which hopefully you can agree with. And then I divide both sides by P of A. And I'm just going to switch them around on the equal signs. So just divide both sides by P of A, I end up with P of A given B times the probability of B over. This sort of gives more confidence that the equation works, because all I've done with these two steps is I've recreated the exact same equation, but this time A and B have swapped. So you can see these are the same, but A and B have swapped around. And that's because A and B are just events that have an impact on each other. So you can say that these two equations are like isomorphic in a lot of ways. A and B just events. There's nothing special about A or B. So this equation can be rearranged into its sort of dual form like this. Cool. So one more small thing about Bayesian statistics, and another sort of real world example, like the medical testing ones, is in crime and guilty verdicts for cases and whatnot. There are a lot of times, well, there are some famous times in history where jurors or judges or prosecutors will misuse mathematics, especially statistics, in prosecuting a case in ways that can be really unfair. And sometimes someone can get later acquitted of something. They get let off because the court realized, well, this math isn't correct. And sometimes it takes bringing in a mathematician or a game theorist or something into a courtroom to explain these things. Let's do an example. So I suppose we'll make it about Todd again. Let's say that, Todd was here on one day. This is Todd. And there's a couple other people around here, right? Let's say there's a lot of people. Maybe he's in Times Square. It doesn't really matter. All right. And there's a bank. And the bank just got robbed. And Todd's been pulled out. He's been suspected, and he's actually under arrest for robbing the bank. They think that Tom robbed this bank, right? They're pretty confident it was him, and now we're on Todd's trail. And let's say that there's some DNA evidence that was left at the scene. And so the prosecutor or whatever says Todd's DNA with the banknotes or whatever are a 1 in 10,000 match. Now, to a naive person on the jury, this sounds like we're saying that there's a 1 in 10,000 chance, or there's a 1 in 10,000 chance that he would be innocent, and then all the other times he'll be guilty. So this is a very condemning fact for Todd, right? It kind of looks like this is the ratio of the odds of him being guilty versus innocent. It's kind of like these are all the ways he can be guilty. These are all the ways that we can be innocent. But people who think this are making this classic mistake of equating this with this. Because this is true that, it's a 1 in 10,000 DNA match. That is quite damning for Todd. But let's say, for example, there are 100,000 people in the area. Well, at least 10 of them are going to have a DNA match, right? So now Todd doesn't look so special anymore. And when they arrested Todd, they knew that his DNA was a match. That's how he ended up in the courtroom. So it's sort of like it doesn't matter. It doesn't really matter what this number is, because no matter what happened, they were going to find someone with a DNA match, because there were enough people to have this happen. So this isn't a fair statistic to bring up in a courtroom, because it's like, there's 100,000 people, 10 of them are going to have this. And these aren't independent events too. They're going to select people who have the DNA match already, so they're already biased. This fact doesn't actually condemn Todd as much as it seems like it does. And there are other examples of this. There was a case once that I read about recently, a British woman who, I think she got suspected of killing two infants of hers or whatever, and then they were twins, and they were looking at what are the odds that two infant twins could just die of natural causes, and meaning that it wouldn't have been murder. And the odds are quite low. It was 1 in a million. And then everyone was like, oh, it's 1 in a million chance that it happened naturally. So in all the other scenarios, it must have been murder. But it's like, well, 1 in a million people. How many people are in the UK? It's 1 in a million. It's bound to happen. It's at some point in the year, but at least maybe 5 or 6 people. I don't know. Those are the people who are going to end up in these trials. So it's actually not that statistically significant, that 1 in a million figure. But it did end up being what put her behind bars, and I think she ended up being found not guilty at some point. So yeah, this way of thinking is not intuitive, but you can teach yourself to think like a Bayesian statistician. I keep this equation in my mind quite a lot. It matters. You might be thinking, you might have heard the term priors. Thinking about your priors. This is like basically all the posterior probability, which is this one here. It's the chance that the thing would have happened before the new evidence. So this is the evidence, and this is your prior. Cool. And yeah, I just think this is a cool part of math. I might do a second video about this because there's a lot of implications with this into like information theory. You can get into machine learning. You learn about how ChatGPT works and all these AI models. This equation is foundational to all token predictors. So there's a lot of places that we can go with this. But yeah, that's all for the video. Cheers for watching, everyone.